This is lecture 4 of differential equations, models, and epidemiology. This lecture is about the next generation matrix. Here's what we're going to do in this lecture. First, we'll introduce a compartmental model for COVID-19 that captures the main features of the disease. Next, using our model, we'll explain the next generation matrix method for calculating R0, a very general method that's used in epidemiology. And third, we'll look at what useful information our formula for R0 gives us. Let's describe a compartmental model for COVID-19. We'll begin with a susceptible category. People in this category can catch the disease. If they do, they move into a category called exposed. In the exposed category, you've got the disease, but so far, you don't have any symptoms, you don't know you've got it, and you're not contagious. Next, people with COVID pass into a category that doesn't seem to have a good name. We're calling it contagious here. Still, no one is showing any symptoms. However, you are infective. In fact, people at this stage of COVID are perhaps the most infective that they ever will be. The first few stages typically last about 2.5 days each. After this stage, two things can happen. Either you develop full-blown COVID, you have symptoms, and we're calling this category infective. It's usually called symptomatic COVID, but it's sort of similar to the category we called infective in previous models. So we'll continue to use that word. If you don't develop symptoms, you develop what's called asymptomatic COVID. Here you've got the disease, but you don't know it. You don't have any symptoms. So people in both these compartments are infective, can pass the disease on to others. Eventually, the disease ends. If you have symptoms, you eventually get better. If you don't have any symptoms, at least you stop being infective. And once the disease is over, you pass into the removed category. And that category includes people who may have died of the disease. So we have 6 different compartments. Let's write down a system of differential equations. There will be 6 differential equations. The variable names are simply the first letters of the names of the compartments. The susceptibles, they decrease as they get the disease and pass into the exposed compartment. At what rate do they get the disease? Well, they can get it from either people in the contagious compartment, people in the infective compartment, or people in the asymptomatic compartment. The betas depend, for example, on how contagious you are, and they depend on how often the infectives come into contact with people. If you're in this category of symptomatic COVID, the infective category, you may be staying home sick, and so you may not be coming into contact with people very often. So there are different betas for each category. The exposed compartment, the size of that compartment grows at the same rate that the susceptible compartment shrinks. And then people pass out of the exposed compartment into the next compartment at a certain rate, proportional to the number of people in the exposed compartment. So this is one of our gammas. It plays the role of gamma in previous models, but we'll put gamma E because the different gammas for the different compartments can be different. So the meaning of gamma E, well, 1 over gamma E is the average length of time you stay in the exposed compartment. That's about 2.5 days. Next, people pass from the exposed compartment into this compartment we called contagious. They enter it at the same rate that they leave the exposed compartment. And then they leave it at a certain rate proportional to the number of people in the compartment. 1 over gamma C is the average length of time you spend in the contagious department. That's also about 2.5 days. These people who leave the contagious department, some percentage enter the infective compartment. The remainder enter the asymptomatic compartment. The percentage that enter the infective compartment we called P, and the percentage that enter the asymptomatic compartment we called 1 minus P. If you added these two terms, you would just get gamma CC. All the people who are leaving the contagious compartment are entering one of these two compartments. For COVID, P is around two-thirds. Around two-thirds of the people who develop COVID go on to develop symptoms. And then finally, people leave the infective compartment at a rate gamma II. They leave the asymptomatic compartment at a rate gamma AA, and both of those groups enter the removed compartment. Here's our system of 6 differential equations. If you were to add the right-hand sides of all these differential equations, as with our previous models, everything would cancel. They'd add up to 0, meaning that the sum of SI dot plus E dot, etc., is 0. And that means that the sum of the population fractions in the different compartments stays constant. Starts off being 1, stays 1. What is the phase space that we'll use for this differential equation? This time, we are not going to take advantage of the fact that the right-hand sides add up to 0 to remove one of the equations. We're just not going to bother. There's not that much advantage to reducing from 6 equations to 5 equations, and it will just turn out to be simpler to understand what's going on to leave all the compartments there. So the phase space is the set of points in this 6-dimensional space, so that each coordinate is at least 0 and the sum of the coordinates is 1. What are the equilibria for this model? Equilibria are the set of points in phase space such that the right-hand side of every single equation is 0. So to find the equilibria, we set the right-hand sides of all these equations equal to 0 and solve. 6 equations and 6 unknowns. How are you going to do that? The simplest way turns out to be to concentrate on the last 4 equations. When I set them equal to 0, I'll have 4 equations in the variables E, C, I, and A. 4 equations and 4 unknowns. And in fact, they're linear equations. The factors multiplying each of the variables are constants in all the equations. If I wrote the system of 4 linear equations in matrix form, I would just have a matrix times the vector of unknowns, E, C, I, A, equals 0, 0, 0, 0. When you have n equations and n unknowns, and you set the right-hand side equal to 0, usually there's only one solution, and that solution is all of the variables are 0. When is there only one solution? If the determinant of that coefficient matrix is not 0, then there's only one solution. All the variables are 0. I'm not going to do it in the lecture. You could check it out yourself. It's partly done in the book. The determinant of that coefficient matrix turns out not to be 0. And therefore, the only solution when we set the last 4 equations equal to 0 is E, C, I, and A are all 0. What that is SR space. The other variables are 0. Our remaining question is everything in that space in equilibrium? And to answer that, we need to look at the first 2 equations. And sure enough, in the first 2 equations, if I set C, I, A, and E all equal to 0, the first 2 equations become 0. So this entire 2-dimensional space, SR space, consists of equilibria. The way you can interpret that is if every single one of these infected categories is 0, you have an equilibrium. You just stay there. The disease doesn't spread. To learn more about the equilibria, what we saw in the last lecture is that we should linearize our system of equations at the equilibrium. So we have 6 equations and 6 unknowns. The linearization matrix will be a 6x6 matrix. So we calculate that 6x6 matrix, and then we really only care about doing this in an equilibrium. And so in that 6x6 matrix, we set E, C, I, and A equal to 0. For example, the first term here in the linearization matrix is the partial of S dot with respect to S. The partial of S dot with respect to S is minus beta C, C, minus beta I, minus beta A. But we want to linearize at an equilibrium. At an equilibrium, C, I, and A are all 0. So at an equilibrium, the partial of S dot with respect to S is 0. When you go through that procedure, this is the matrix you get for the linearization at an equilibrium. It depends on the S coordinate of the equilibrium. That's all it really depends on. By the way, the last column here is the partial of S dot, E dot, C dot, et cetera, with respect to R. You don't see any R's in any of these equations, so these are all zeros. What we saw in the last lecture is that to learn about equilibria, it helps to linearize at them and then find the eigenvalues. So let's try and do that. We subtract lambda from each diagonal term in our 6x6 matrix, take the determinant, and set it equal to 0. Perhaps you remember something about evaluating determinants of big matrices. It often helps to expand by a row or a column. Here, I think I begin by expanding by the first column because of all those zeros. What we'll get is minus lambda times the determinant of this lower 5x5 matrix, plus a bunch of zeros. That factor minus lambda is going to produce a 0 eigenvalue. Now we have to evaluate this lower 5x5 determinant. And I think I would begin by expanding by the last column because of so many zeros. We'll end up with another minus lambda times the determinant of this inside 4x4 matrix. That second minus lambda produces a second eigenvalue, 0. So the eigenvalues are 0, 0, and then the solutions of finding the determinant of this 4x4 matrix and setting it equal to 0. In other words, what we find if we go through all that is the eigenvalues of this interior 4x4 matrix without the lambdas. Call that matrix K. So the eigenvalues are 0, 0, and the eigenvalues of K. Let's summarize where we stand. Our model for COVID-19 has a two-dimensional subspace of equilibria, SR space, that's the equilibria. And each of those equilibria has at least 2 0 eigenvalues. A couple comments. These equilibria are not hyperbolic. Nothing we learned about hyperbolic equilibria is going to apply because of the 0 eigenvalues. That's the first observation. The second observation is if you have a k-dimensional subspace of equilibria, you're always going to have at least k 0 eigenvalues. That's why with a two-dimensional subspace of equilibria, we're always going to have at least 2 0 eigenvalues. Now it's time for a little differential equations theory. Normally hyperbolic equilibria. Suppose the differential equation x dot equals f of x on Rn has a k-dimensional subspace E of equilibria, or more generally a k-dimensional manifold of equilibria, but we don't need to go there. An equilibrium x naught in that subspace is called normally hyperbolic if the matrix df of x naught has exactly k 0 eigenvalues. It always has at least k 0 eigenvalues. And the remaining n minus k eigenvalues all have non-zero real part, like in a hyperbolic matrix. The remaining eigenvalues, none of them are zero and none of them are pure imaginary. What good does it do to know that an equilibrium is normally hyperbolic? Here's a theorem that tells us some of what's going on at normally hyperbolic equilibrium. Suppose the differential equation, x dot equals f of x on Rn, has a k-dimensional subspace E of equilibrium. They may not all be normally hyperbolic, but let E naught be an open subset of E such that all the equilibria in E naught are normally hyperbolic. And we'll suppose that for all x naught in E naught, df at x naught has L eigenvalues with negative real part and M eigenvalues with positive real part. One of those numbers might be zero. And of course, we'll have K plus L plus M equals N, the dimension of the space, because all of the eigenvalues are either the K eigenvalue 0, the L eigenvalues with negative real part, or the M eigenvalues with positive real part. That's what would happen at a normally hyperbolic equilibrium. Then what are our conclusions? First, each x naught in E naught has a stable manifold, Ws of x naught, of dimension L, the number of eigenvalues with negative real part. The stable manifold consists of solutions that head toward the equilibrium x naught in future time. Second, each x naught in E naught has an unstable manifold, Wu of x naught, of dimension M. M is the number of eigenvalues with positive real part. And this manifold consists of all the solutions that approach x naught in backwards time. Third, the union of all the stable manifolds of x naught is called the stable manifold of the set E naught, and its dimension is K for the dimension of the underlying open set E naught, and L for the number of stable eigenvalues. And finally, the union of the manifolds Wu of x naught is a manifold called Wu of E naught of dimension K plus M, K for the dimension of the underlying open set E naught, M for the number of unstable. Both of these words should be is. That was probably all pretty confusing. Let's see what that theorem means for our old friend, the SIR model. Here's the SIR model reduced to just two equations. And you may remember, here's the phase portrait for R naught less than 1. Here's the phase portrait for R naught bigger than 1 in the triangle. First of all, in both cases, there's a one-dimensional space of equilibria. It's I equals 0. There it is. Second, in the case R naught less than 1, it turns out that all these equilibria are normally hyperbolic. The other eigenvalue is negative. So they all have a one-dimensional stable manifold. There they are. And the union of all these manifolds, the dimension is 1 for the space of equilibria, 1 for the dimension of the stable manifolds. 1 plus 1 is 2. Put them all together and you get a two-dimensional set, an open set in the plane. For R naught bigger than 1, it's not true that all the equilibria are normally hyperbolic. They are all normally hyperbolic except the equilibrium at S equals gamma over beta. To the right, their other eigenvalue is positive. And to the left here, their other eigenvalue is negative. So over here to the right, each equilibrium has a one-dimensional unstable manifold. Put them all together, you get a two-dimensional set. Here to the left, each equilibrium has a one-dimensional stable manifold. Put them all together, you get a two-dimensional set. Now we're going to spend a few minutes looking at the equilibria of our COVID-19 model and trying to figure out whether they're normally hyperbolic or not. We're only going to partly figure this out at this point. Equilibria of the COVID-19 model are normally hyperbolic if that matrix K that we look at has no zero eigenvalues and no pure imaginary eigenvalues, no eigenvalues with real part zero. So let's just look at it a little bit and see what we can figure out. Let's start down here. Let's look at an equilibrium with S equals 0. When S is 0, these three terms become 0. So then all the terms above the diagonal are 0. If you have a matrix where all the terms above the diagonal are 0, or a matrix where all the terms below the diagonal are 0, then it's really easy to find the eigenvalues. They're just the diagonal entries of the matrix. In this case, all 4 eigenvalues are negative. And the determinant, which is always the product of the eigenvalues, multiply 4 negative numbers together, you get a positive number. So at S equals 0, the eigenvalues are all negative, the determinant is positive. Now, as I increase S, the eigenvalues can change. One of them can become 0 when the determinant becomes 0, because the determinant is the product of the eigenvalues. So let's just look at the determinant of this matrix. That's a lot easier to figure out than all the eigenvalues. You can multiply everything out to get the determinant of the matrix. I won't do it in the lecture, it's done in the book. And here's what you find out. The determinant turns out to be 0 at exactly one value of S. S equals S naught equals 1 over this expression. When S is less than S naught, the determinant's positive. And that's consistent with what we found before at S equals 0, where all 4 eigenvalues were negative. That produced a positive determinant. When S is greater than S naught, the determinant becomes negative. So let's take a guess at what's going on here that's consistent with this information. Here's our guess. For S less than S naught, let's guess that just like at S equals 0, all the eigenvalues are negative. Multiply them together, we get a positive determinant. At S equals S naught, the determinant becomes 0. The simplest way that can happen is if just one of the eigenvalues becomes 0. For S greater than S naught, we know the determinant becomes negative. The simplest way that can happen is if that one eigenvalue that became 0 moves over and becomes positive. Then we would have 1 positive eigenvalue, 3 negative eigenvalues, and if you multiply them together, you'd get the negative determinant. So that's our guess as to what happens. Now, by the way, can an epidemic start near an equilibrium by increasing the infectives a little? If this picture is right, near an equilibrium with S less than S naught, where all the eigenvalues are negative, if you move away from that equilibria, because of the picture we have for normally hyperbolic equilibria with all negative eigenvalues, you're just going to move back immediately to a nearby equilibrium, and the epidemic would die out. For S greater than S naught, with 3 eigenvalues negative and 1 positive, could a disease start near that equilibrium? You bet. That 1 positive eigenvalue is enough to do it. You'd have a 3-dimensional manifold where you're attracted to the equilibrium, a 1-dimensional manifold where you're repelled, and almost every solution, the ones not in that 3-dimensional manifold, are going to go along toward the equilibrium and then away from it in the unstable direction. So this one positive eigenvalue would be plenty to allow epidemics to start. kind of like this picture here. Assuming that transition point S0 was small enough to be in the set we're interested in, what we're finding is that for S to the left of it, epidemics would die out. For S to the right of it, epidemics could start. The next thing we're going to do is look at the next generation matrix, which is a method for computing R0 in complicated models of epidemiology, like the one we've got. And it also gives information about the stability of all those other equilibria. We're going to try and describe how you compute R0 in a way that applies to all kinds of models, but the example that we'll always be referring to is our COVID model. To calculate R0 for a complicated epidemiological model using this method, you begin by linearizing at the equilibria, and then you look at the submatrix K that just has one row and one column for each infected compartment. So in our model, we're going to ignore the susceptible compartment. We're going to ignore the removed compartment. And I very carefully wrote infected, not infective. That exposed compartment in the COVID model consists of individuals who are infected, but they're not yet infective. The disease is developing, they can't yet infect anyone. In our COVID model, the infected compartments are E, C, I, and A. Those are the middle four of the variables. And the matrix K is exactly that thing that we calculated earlier and called K, whose eigenvalues we said would be important for determining if an equilibrium was normally hyperbolic or not. The next step in calculating the next generation matrix is to decompose the matrix K into a difference of two matrices in a certain way. The first matrix F is going to be the ones with these beta S terms. And then the next matrix V will be everything else. And because we're putting a minus sign in, all the signs here are the reverse of what they were before. How did I decide what to include in F and what to include in V? F is all the terms that have to do with transfers into an infected compartment from an uninfected compartment. In this case, there'll always be transfers into an infected compartment from the susceptible compartment. V has to do with all other transfers, transfers between two infected compartments or transfers out of the infected compartments altogether. In our model, that would be to the removed compartment. Let's look at the matrix F in more detail. The entry Fij is a rate of transfer from uninfected compartments. In our case, there's only one, but there could be lots, into infected compartment I that is due to infection by people in infected compartment J. It's a rate, so per unit time, but it's also per population unit. So what we have to do with the matrix F to see what it means, if we multiply the matrix F by a vector of population fractions in the infected compartments, what we'll end up with is the rate of transfer from uninfected compartments into infected compartment I that is caused by those population fractions. So let's look at that. F times a vector of population fractions in the infected compartments. So that's this matrix times this vector. And here's what we get. For the first entry, we get this row times this column. There's what we get. The other entries are all zero because these guys are zero. What does that mean? The rate of transfer into infected compartment E from uninfected compartments caused by these population fractions right here is this sum. Beta CSC is the transfer caused by people in infected compartment C. Beta ISI is the transfer caused by people in infected compartments I. Beta ASA is the transfer caused by people in infected compartment A. They're all giving the disease to susceptibles. Susceptibles, when they catch the disease, always transfer into compartment E. That's why all these other entries are zero. No matter how many effectives are running around, susceptibles never transfer into these other compartments. Now let's look at the meaning of V. Remember the minus sign in the definition of V. The entries of F told us about transfers into infected compartments. The entries of V are going to tell us about transfers out of infected compartments because of that minus sign. Vij is the rate of transfer out of infected compartment I due to people in infected compartment J per population unit. If you multiply V by a vector of population fractions in the infected compartments, what you will get is the rate of transfer out of infected compartments caused by those population fractions. Very similar to the definition of F. To keep things from getting too complicated, we'll look at a vector of population fractions with nobody in compartment C and nobody in compartment A, and we'll multiply it by V. So here's V times our vector of population fractions, and here's the result. For example, the first row times this vector gives just gamma E times E. The rate of transfer out of compartment E caused by people in these compartments, in this case, the people in compartment E itself, is gamma EE. The rate of transfer out of compartment C, well, because of the minus sign, it's really a rate of transfer into compartment C, and it's caused by those people in compartment E. They're transferring into compartment C, minus gamma EE. The rate of transfer out of compartment I is gamma II. It's just caused by the people in I. And there is no corresponding term with a minus sign because the people in this compartment, the compartment with full-blown symptomatic COVID, when they transfer out of this compartment, they don't go to another infected compartment, they go to the removed compartment. So there's no corresponding term with a minus sign. We're gradually building up to defining the next generation matrix. We haven't got there yet. The next generation matrix makes use of V inverse. So what is V inverse? You've probably encountered it in the linear algebra class. If you haven't, V inverse is the matrix that you multiply V by to get I. You have probably learned how to calculate V inverse. If you haven't, I'll just tell you what it is. Here's V up here, here's V inverse down here. Even if you don't know how to calculate it, you can check that it's correct. The way to check that it's correct is to just multiply V by V inverse and make sure that you get the identity matrix. That's the matrix with ones down the diagonal and zeros elsewhere. So for example, if I multiply the first row by the first column, I'll just get 1. And that's what the upper left-hand entry of the identity matrix is. You could check out all the entries. What does V inverse mean? If you looked at these numbers for a little while, you could probably figure it out. V inverse Ij is the mean time spent in infected compartment I if you started out in infected compartment J. So in other words, each column of this matrix gives you the mean time spent in the different infected compartments if you started out in the infected compartment represented by that column. Let's look at the first column. The first column corresponds to infected compartment E, the exposed compartment. If you start in infected compartment E, here's how you end up spending your time. You spend time 1 over gamma E on average in compartment E. Then you move into compartment C. You spend time 1 over gamma C in that compartment. And then there's 2 possibilities. If you move into compartment I, you spend time 1 over gamma I there. If you move into compartment A, you spend 1 over gamma A time there. With probability P, you move into compartment I. With probability 1 minus P, you move into compartment A. And so these numbers simply give you the expected time that you will spend in the different compartments if you start in infected compartment E. And the other columns are exactly the same. We haven't proved that in general. That would take us a bit afield. It's done in the book. So now we're ready to define the next generation matrix with all that preparation. The next generation matrix is simply the product F times V inverse. Here's F. Here's V inverse, familiar from the previous slides. And now let's multiply them out. These 3 rows are going to turn out to be just rows of zeros because of the 3 rows of zeros here. What about the first row? Okay, so the first entry will be first row here times first column here. And here's what you'll end up getting. Beta CS over gamma C plus these other terms. Now we still have to figure out the first entries here, but they're not going to be that important to us, so I'm not actually going to figure them out. I just put asterisks there. So that's the next generation matrix, FV inverse. What does it mean? Why in the world did we calculate it? Now we have to think about how matrix multiplication works. What is FIK, the IK entry of F? It's the rate of transfer from uninfected compartments into infected compartment I that is due to infection by people in infected compartment K per population unit. It's a rate per unit time. What's V inverse Kj? This is one of the things you would multiply FIK by when you calculate the matrix product. It's mean time spent in infected compartment K if you start in infected compartment J. So when I multiply these 2 numbers together, what I'll have is a rate times a time. That will give me total mean transfer, not a rate anymore, total mean transfer from uninfected compartments into infected compartment I due to the time spent in infected compartment K infecting people by individuals initially in infected compartment J. So I say that again. FIK times V inverse Kj. It's a rate times a time, so you get a total mean transfer from uninfected compartments into infected compartment I, caused by the time spent in infected compartment K infecting people by individuals who started out in infected compartment J per population unit. This first paragraph just repeats what we said. And now to get the IJ entry of FB inverse, we look here, we fix I and fix J and sum over K. So we're fixing the infected compartment that the people in the uninfected compartments are transferring into. We're fixing that. We're fixing compartment J, the compartment that these people started in, and we're summing over all K. We're summing over all the different infected compartments where those people might be spending time. So when you sum over K, what you get is total mean transfer from uninfected compartments to infected compartment I, caused by individuals who started in infected compartment J over the entire time that they remain in all the infected compartments per population unit. We'll look at an example in a minute, but let's finish up here with the generalities. So what's the definition of R naught? If we were to multiply FV inverse by an initial vector of population fractions in the infected compartments, we would get the vector of new infections caused by the people who started out in those compartments over all the time that they spend in the different infected compartments infecting people. What's interesting is, did they infect more people than there were of them or less? That's what we're always interested in. Just look at the size of this vector, the size of the vector here, which is like the square root of the sum of the squares of the entries. The size of this vector of new infections is going to be some multiple of the size of vector of old infections. And for a non-negative matrix, which FB inverse always turns out to be, the maximum value of this multiple is the largest eigenvalue of FB inverse. And since what we're interested in for R naught is how many new infections can be caused by old infections, we're going to define R naught to be the largest eigenvalue of FB inverse for S equals 1 when everybody starts out being susceptible. The largest eigenvalue is, in effect, the biggest number of new infections that can be caused by some original infections. Let's relate this to our first 3 lectures. In our first 3 lectures, there was only one infected compartment. FB inverse is just a product of 2 numbers, 2 1-by-1 matrices. For the matrix F, you'd end up with beta S. For the matrix B inverse, you'd end up with 1 over gamma. And when you set S equal to 1, you get beta times 1 over gamma, which is R naught. This is a generalization of the formula for R naught we used for simpler models. Let's see how this works out for the COVID-19 model. FB inverse, we already calculated. This is the matrix we got. It's a matrix with all zeros below the diagonal. Therefore, the eigenvalues are the diagonal entries. So they are this number and 3 zeros. As long as S is greater than or equal to 0, which it is in our phase space of interest, the largest of those 4 eigenvalues is simply going to be this number. And if we set S equal to 1, we'll get R naught, which is this expression here. Let's pause for a minute to see how R naught is related to eigenvalues and eigenvectors. So we're going to figure out the eigenvector for the largest eigenvalue FB inverse. So we set S equal to 1, and actually the eigenvector is just 1, 0, 0, 0 for that eigenvalue. But let's just check by multiplying it out. FB inverse times 1, 0, 0, 0. So that's our matrix FB inverse times 1, 0, 0, 0. So multiply the first row times this column, and we'll just get this number times 1. Whoops, I left the S in there. S should be 1. The other entries are the other rows times this matrix. They're all zeros. So this is what we get when we multiply FB inverse times 1, 0, 0, 0, except that the S's should all be 1s. And if I factor out this number, it's just this number here times the vector 1, 0, 0, 0. That's what an eigenvector is. When you multiply your matrix times a vector, you simply get a multiple of that vector, and the multiple is the eigenvalue. Now, does this make sense? What this calculation is saying, let's interpret this as one person in the exposed category. Really means a population fraction of one, but let's interpret it as one person in the exposed category. And then this follows him over all the times he spends in the different infected categories, infecting people until he leaves and goes to the removed category. And the calculation tells us the result. The result is some new people in the exposed category, this number of people. Why is it this number of people? Well, while he was in compartment C, the number of people he infected would have been beta C times 1 over gamma C. While he was in compartment I, the number of people he would have infected would have been beta I over gamma I, but he's only there with probability P. And while he's in compartment A, the number of people he would have infected would have been beta A over gamma A, and he's there with probability 1 minus P. This is the total number of people that he infects. And they end up in compartment E. I mentioned that this next generation matrix tells us something about all the equilibria. So the largest eigenvalue for S equals 1 is this expression. We call it R naught. The largest eigenvalue for other S's, S greater than or equal to 0, it was the same expression, but with S's everywhere. In other words, it was this expression times S, R naught times S. So what? Well, we have a nice theorem here. In the compartmental models of epidemiology, at a normally hyperbolic equilibrium, all the non-zero eigenvalues have negative real part if and only if the largest eigenvalue of the next generation matrix at the equilibrium is less than 1. So for our equilibria, this eigenvalue is less than 1 if S is smaller than 1 over R naught. It equals 1 if S equals 1 over R naught. And it's greater than 1 if S is greater than 1 over R naught. So this number 1 over R naught separates the equilibria where an epidemic will die out from the equilibria where an epidemic can grow. And this information corresponds exactly to the information we got at the beginning when we looked at eigenvalues. This turns out to be exactly that place where the determinant was 0 and you switched from attracting to a positive eigenvalue. It's all consistent. What does R naught tell us that might help us control an epidemic? For an epidemic like COVID-19, we might have estimates for all these different numbers. We'd get an R naught that's 3 or 4, something like that. Actually, it depends on the variant that you look at. And we might ask, if we institute control measures, how will that affect R naught? Can we get it under 1? So let's look at a few control measures that might be used. What about temperature checks, like when you enter a shopping mall or a restaurant? What's a temperature check going to do? Temperature check will determine whether an individual has full-blown symptomatic COVID, whether he's in the compartment we call I. If you turn up such an individual and you don't let him into your restaurant or your shopping mall, tell him to go home, what you're doing is reducing the number of people that he's going to contact because you're sending him home. So you're reducing beta I. The trouble is that if he had symptomatic COVID, he probably knew he was sick anyway and was probably staying home anyway. But there might be some people that this would help with. So this might reduce beta I a little. What about if you simply order a quarantine? All sick individuals should stay home. The sick individuals are the ones in compartment I. Telling them to stay home would reduce the number of people they contact. So you might also be reducing this beta I a little, but probably they're staying home anyway because they're sick. What about contact tracing? Nice thing about contact tracing is, you know somebody's sick, you look at all the people he's been in contact with, you might find some of them before they develop full-blown infected COVID. You might find some of them who never develop full-blown infected COVID because they become asymptomatic. Contact tracing takes time. You're probably not going to turn people up until they've passed through compartments E and C and into the asymptomatic compartment. So by finding those people and telling them to stay home or encouraging them to stay home, you might succeed in reducing beta A. And this is kind of important because those asymptomatics, they don't know that they're sick. They would be going around doing what they normally do. If you can get them to stay home, that will help. Another possible control measure is encouraging mask wearing by everyone. That helps reduce all the betas, especially these people in the contagious department and the asymptomatic department who are wandering around when they don't know they've got COVID. If they're wearing masks, they are less likely to actually transmit the disease. So the masks are affecting the betas by affecting that probability of transmission of the disease, not by affecting rates of contact. And it also helps to have everybody else wearing a mask. That also helps reduce the probability of transmission a little bit. What about a lockdown, the most desperate measure of all, telling everybody to stay home? Not everybody will, but a lot of people will. Lockdowns reduce all the betas. They reduce average numbers of contacts across the population. So you can look at the numbers and see what you might get out of all these measures and see whether you're succeeding in getting R naught below 1. See what you need to do to get R naught below 1. That's the end of the lecture. Thank you very much for listening.